Einstein had said many, many years before that, in 1916, he already said that when he made some numbers for himself about gravitational waves, at the very end, by the way, this paper is on the web, translated into English, so anybody can go look at it. It's the 1916 paper on perturbation expansions of the general relativity, of the equations of general relativity, where he does certain calculations. He shows that you get the perihelion advance for Mercury. He shows that it makes Newton's physics in the limit of weak fields. And for the first time in his life, Einstein talks about gravitational waves, pretty much with what I just showed you. But what he gets very wrong, by the way, is how the sources make the waves themselves. He gets that wrong, not in the quantitative way, but in a qualitative way. In fact, I'll tell you what happens in that paper. He thinks, because of the way he formulated the equations, that what makes gravitational waves is he clearly saw that gravitational waves were being made by objects very much like electromagnetic waves are made by acceleration of charge. He saw that they were made by acceleration of matter. So a thing that goes smash into each other, that makes gravitational waves. Two things going around each other in orbit, they make gravitational waves. And that was honest stuff, and he had it right. But he also made a prediction there, because of a mistake he made, that things that are uniformly expanding and contracting, like a soap bubble, you blow it up, suck it up, blow it up, suck it in, blow it up, that would also radiate. And that's not true. That's monopole radiation. That would not be quadrupole radiation. So it turns out that he screwed up, but he did at the end of that paper, the numbers that he had, the powers of C that were involved, the powers of big G that were involved, the powers of frequency that were involved. All of that was about right. And he plugs us in just like you or I would. I've asked the Einstein people to go find the back of the envelope he used. They claim there isn't one. I'm sure there is one. Because he didn't put it in his paper. He didn't put the calculation in his paper, but he only puts the result in. He says that when you look at that equation, what is in at the end of the paper, and you put the numbers into it, you'll find out this will never play a role in physics at all. And you have to think what Einstein might have known. And I want to see I did the calculation for him, because I was curious what he might have done. He probably had, what's the biggest thing he could imagine in 1916? Two trains smashing into each other, okay? Well, two trains smashing into each other, you do that calculation using the elemental formulae that Einstein had, and they were right, the formulas were almost right. You would get, in the radiation zone, which is about 300 kilometers away, in a collision like that, you have to get away from the induced field. You have to get out into the radiation zone. So at least one wavelength away. And for the times involved, it's about 300 kilometers away. At 300 kilometers, when these two trains smash into each other at 100 miles an hour each, it's a pretty good collision, killing a lot of people. The thing has only got a strain, as measured at that distance, of 10 to the minus 42. Okay? So that was clear that Einstein said this is never going to be measured by anybody. And so then he probably thought of something else. He probably thought of binary stars. They were known. I mean, they were not known the way we know them. We know of little compact binaries, which are very important. But there are binaries in our own galaxy, which are made of ordinary stars. Well, white dwarf stars. So those are electron degenerate stars, and they're electron degenerate object. It's pretty small. It's much smaller than the sun. Has the mass of the sun, but it's much smaller.
Yeah, that's right.
And so two white dwarfs going around each other could have a period of 8 hours without tearing each other apart, or even, yeah. And how long would you have to wait if you looked at one with a telescope for the thing to see that's losing energy by them falling toward each other and the waves coming out? You're not going to see the waves, but you should see the loss of energy into the waves. And you make the number and you'll find out it takes something like the age of the universe to see a change. So, it was hopeless. And that's why Einstein wrote, it's never going to play a role. And so here this guy, who was a little bit nutty, decided to challenge that. And he made an experiment which was only a factor of 1,000,000 off the mark. His sensitivity was 10 to the minus 16 strain. You had to be, we did it, and later on, Kip and others, as I told you, had 10 to the minus 21. And that, it's 10 to the minus 15, that's about 1,000,000 in strain. So in energy, it's 10 to the 10 they were off, okay? 10 to the 12. It's 10 to minus 6, 10 to minus 12, yeah. So it looked pretty dismal.